All right, guys, let's get into some trig identities. So let's first just kind of introduce what an identity is. Let's look at a couple algebraic expressions, equations here, and see which ones are identities. So if we take a look at the equation in part A there, so x plus 3 times x minus 1 equals x squared plus 2x minus 3. So, I mean, I guess we could kind of check we know how to FOIL this out, x squared, then minus x, then plus 3x, and then minus 3, and that would simplify to x squared plus 2x minus 3, okay, which kind of is what the other side is. So this seems to be like a true statement, right? Let's move on and we'll come back to them. What about B? 2x plus 5 equals x plus 10. I guess we could solve for x maybe, subtract x from both sides. Get x plus 5 equals 10, and then subtract the 5, get x equals 5. So, I mean, we kind of solved an equation here. And then part C, sine over cosine equals tangent. I know we've used that, with the unit circle and all that stuff, y over x equals tangent. So, I mean, that one seems to be true. Okay, so any ideas on what it means to be an identity? Okay, so really what it boils down to here, an identity is going to be something that is true for all values in the domain. Okay, so true for all values in the domain. So for example, part A, that expression is true for all real numbers, right? We basically just did multiplication on the left side and it ended up equaling the right side. So no matter what x we put in, that statement's true. Those sides will be equal. Okay, so that is an identity. Part B, is this thing always a true statement? And the answer is no. It's only true if x equals 5. So this one is not an identity, but it's just a normal equation. It has a solution, but it's not going to be considered an identity. And then part C, sine x over cosine x equals tangent x. That's going to be true for all x values for which x is defined. Okay, so for sine and cosine, they're always defined. Tangent does have some restrictions on it, basically whenever cosine is 0. But that's going to be true, so that is actually an identity. And that's an example of a trig identity. And I just want to kind of get into what do they do for us, why do we need them, how can they help us? So let's look at a sample problem here. Just imagine there's like let's say you have like a box or something that's sitting on a ramp, okay, and you want the box, you're trying to get it to slide down the ramp, okay? So let's jump down here first. So for this, for a different surface, okay, there's always going to be some sort of friction, if the surface or the ramp was made out of ice, versus being like sandpaper, it would be different. So let's just say for this surface, the coefficient of friction is just a value to measure the friction. It's not going to be important for us, but in this little example, it plays a role. So let's just say that coefficient of friction for that, whatever the surface is 0.14. Okay, and the box will slide down whenever the angle, so we have this angle here, theta, okay, and the greater that angle gets, it's more likely the box will slide down because it's a steeper slope. So the box will slide down when the angle theta is large enough so that m times g, so the mass of the box, okay, and the gravity times sine theta equals that coefficient of friction times mass, gravity, cosine theta. So again, this is more like just a physics kind of example. I'm just using it to introduce why an identity is going to be helpful. So don't worry if the m and the g and all that stuff doesn't ring a bell. Anyway, so let's think about this equation. Can we solve it for theta? Okay, so what we could do, we could divide both sides by the mass and gravity, and that's going to actually cancel out on both sides. So that's kind of a nice little simplifier. So we would just be left with sine of theta equals this coefficient of friction, which they're telling us is 0.14, cosine theta. Okay, so let's see, how can we solve that? There's two functions in there, right? There's sines and there's cosines in there. So what we could do, we could actually divide both sides by cosine theta, get rid of that. Okay, let me just pick this up here where we have some room. We now have sine theta over cosine theta equals 0.14. Okay, now are we able to solve that? So can we find, the variables in there twice? There's two thetas in there. There's two trig functions in there. I don't really know what to do with that. But if we go back to the fact, we know what sine of theta over cosine of theta, we know that equals tangent of theta, doesn't it? Okay, so we have tangent of theta, okay, using the trig identity, right? There's a trig substitution. This sine over cosine equals tangent. Okay, we are now able to solve this thing. Okay, we need a calculator to do it, but we could actually finish this out now if we wanted to. We could take the inverse tangent of both sides, and on a calculator we could input that and get a value. Okay, so I just did that in a calculator there. I did the inverse tangent of 0.14. I went back to degree mode. We were probably in radians from what we were doing before. But it's right around 7.97 degrees for this one. So that would be, how large the angle would need to be to get this box to slide down that surface. Okay, and again, it's a very physicsy type problem. I'm just doing it, the thing we're going to be doing in pre-calc here in math. It's kind of recognizing that, making that substitution, knowing that trig identity, that sine over cosine equals tangent, it just opens some doors for us. Okay, it will be a way to get in a problem, instead of having a bunch of different trig functions, you can simplify it down to a single trig function, or maybe a much simpler expression. All right, so let's take a look at one of the main identities. What I want to do, I actually put in Desmos here. You'll see the graph. I graphed sine squared x plus cosine squared x. And just note the way that it's written here and here, it is not this. It is not the same as sine x squared. Okay, we're not squaring the angle. Okay, we're actually squaring the sine of the angle. So it could be written this way if you want. It's kind of common to write the squared before the x, but again, it's not the angle, it's not the x that's being squared, it's the sine of the angle and the cosine. So in Desmos, you'll see I put the extra parentheses around there. I wasn't able to get the squared before the x, but anyways, that's what's going on. So if you take a look, the graph is shown here, and it's actually a straight line going through y equals 1. Okay, and it's showing that no matter what the x value is, and I'm fairly zoomed in, but if you zoomed way out, it's going to stay a constant value of 1 the whole time. Okay, so it appears that sine squared of any angle plus the cosine squared of any angle is going to equal 1 based on what this graph is showing. Okay, now the graph isn't necessarily like a full proof, but it's a good visualization, and that is actually an identity, and that's the main Pythagorean identity. This can be a big one here, is that sine squared of any x plus cosine squared of the same angle, x, will always equal 1. That is an identity. Okay, I'll prove it to you guys in a second here. We'll do an example. But that is the Pythagorean identity. Okay, if you think Pythagorean theorem, a squared plus b squared equals c squared. That's pretty much what's going on here. Let's take a look at the proof on that and then see what it can do for us. Let's throw a new blank page in here. So we're saying sine squared plus cosine squared equals 1, right? So sine squared of an angle plus cosine squared of an angle. Okay, let's, I'm telling you guys it equals 1. So if we go back to definitions, and I'm just trying to kind of prove this identity. So sine is opposite over hypotenuse. Okay, so if that's squared, that's sine squared of any angle. Cosine of an angle is the adjacent side over the hypotenuse squared. Okay, and when you square a fraction, you square the numerator and the denominator. Okay, so we're kind of just algebraically simplifying here. Okay, two fractions are being added together. We actually have a common denominator of hypotenuse squared, so that's good. Okay, so opposite squared plus adjacent squared. Okay, and if we think about this, let's just kind of visualize any old random triangle there, right? Let's say we have the opposite side over here, we have the adjacent side down here, and of course the hypotenuse, right? And if we take a look, the opposite side squared plus the adjacent side squared, based on Pythagorean's theorem, we know the opposite side squared plus the adjacent side squared is the hypotenuse squared, right? That's Pythagorean theorem right there. So the numerator is the hypotenuse squared, and the denominator is the hypotenuse squared. Okay, thus, this will always equal 1. Okay, doesn't matter what the angle is, doesn't matter what the triangle looks like, based on Pythagorean theorem, right? That's why this is Pythagorean identity. This always equals this. Okay, so that's just straight up Pythagorean theorem. Okay, so we're going to be able to use this identity quite a bit, and it's going to have a lot of different variations and rearrangements. It's going to show up in a lot of problems. Okay, so let's take a look. Okay. All right, so the identity we just derived is the Pythagorean identity. If you take a look at example A here, they are going to give another variation of it. So let's walk through what they did here. So here's the basic given identity that we just used. Okay, if you were to divide every term by cosine squared, okay, dividing all three terms by cosine squared, so you get sine squared over cosine squared, which is tangent squared. Okay, cosine squared over cosine squared is 1. And then 1 over cosine squared, remember the reciprocal of cosine is secant, so 1 over cosine squared is secant squared. So this right here, this is another kind of like a variation on the Pythagorean identity. It's not the main one, okay, this up here is the main one, but it comes directly from that. And if you ever forget it, you can always just remember to divide all of the terms by cosine squared and you'll get it. Okay, because there's going to be quite a few in this list, and you don't really need to memorize everything. You definitely need to memorize this main one, though. Okay, and let's talk about now one other one that comes from that in a similar way. Okay, let's start out again with the big dog, sine squared plus cosine squared equals 1. Okay, and in the first example, we divided by cosine squared. This time, let's divide everything by sine squared. Okay, and these are really the only two options. You're not going to have to divide by everything. So if you just remember these two, if we divide all the terms by sine squared theta, let's see what we get. Okay, so the first term, sine squared divided by sine squared, something divided by itself is 1. Okay, cosine squared over sine squared is cotangent squared. Okay, because remember sine over cosine is tangent, right? So this is the reciprocal of that. And then 1 over sine squared is cosecant squared. Okay, so we now have two variations. Here's the second one that we did a few minutes ago. Here's the third one. Okay, and those are all going to be identities or things that we can use to simplify expressions and solve equations and do a whole bunch of things with. Okay, so both of those, again, just came from knowing this main one. And as long as you can divide them by cosine squared or sine squared, you can get new identities. Okay, and those are really the three. Now, there's different rearrangements of these that you're going to want to be familiar with. But these are the three main ones. So we'll talk more about that in just a second. Okay, let's get a little list going here. Okay, we have some quotient and reciprocals, some things that we've been using already. The reciprocal identities, okay, so sine, the reciprocal of sine is cosecant, so sine theta always equals 1 over cosecant. And similarly, cosecant equals 1 over sine. That's just what it means to be a reciprocal. Okay, cosine of theta is the reciprocal of secant. And thus, secant is the reciprocal of cosine. Okay, now tangent can be written two ways. Tangent, the more common way that we've seen is sine over cosine, but it's also a reciprocal of cotangent. So tangent is also 1 over cotangent. Okay, and just to finish it off, cotangent is the reciprocal of tangent, so it's cosine over sine, or 1 over tangent. Okay, so there's a little list. There's a few things we're going to be using. Okay, and then the three main Pythagorean identities. The big one, the sine squared x plus cosine squared x equals 1. Okay, and I noticed I was using theta above and x here. They're kind of interchangeable for the angle. But sine squared plus cosine x, sine squared plus cosine squared equals 1. If I divided them all by sine squared, I would get 1 plus cotangent squared equals cosecant squared. Okay, this is the one from a few minutes ago. And then if I divided the original by cosine squared, I would get tangent squared plus 1 equals secant squared. Okay, so those are the big ones. Now again, there are going to be different arrangements, different orders of these things. For example, we could think about from this first one here. If let's just say I wanted to subtract, let me just rewrite the original, sine squared plus cosine squared equals 1. It would also be true then that if I subtracted cosine squared from both sides, sine squared would equal 1 minus cosine squared. So that could be thought of as like another one, right? It's just a variation. And the reason that might be helpful, you might in a problem somewhere see, let's just say you're working through a problem and sine squared shows up. Okay, you're going to know that 1 minus cosine squared is equivalent to it. So my advice again is to memorize this one, like just know it. Be able to come up with these two by doing the division. And then once you kind of know which terms are showing up in your problem, then be able to do all the rearrangements so that you can correctly substitute in something you need to substitute in. Okay, and these again will be done for two things. We're going to be able to simplify expressions and then also verify other identities using these.